Good morning, friends. Last time we discussed about the properties of impedance, characteristic impedance, and today we will continue that and discuss about design of filters. Now, we saw last time cosine beta was 1 plus Z1 by twice Z2 when alpha equal to 0, that is in the pass band. This means because beta is cosine beta is between -1 and +1. So, we can write -1 1 plus Z1 by twice Z2 less than equal to 1. If I subtract 1 from all the three, then it reduces to Z1 by 4 Z2 less than equal to 0. Okay. Now, in the stop band, we have where alpha is not equal to 0, we put the other condition sin beta sin hyperbolic alpha equal to 0. Okay. That means there are two possibilities. If sin beta equal to 0, then beta can be either 0 or plus minus pi. If beta is 0, then cos hyperbolic alpha, that is cos alpha, is 1 plus Z1 by twice Z2, and if beta equal to plus minus pi, then minus cos alpha equal to 1 plus Z1 by twice Z2. This we saw last time. So, from here we can find, if I take Z1 by 4 Z2 along this x axis, then between 0 and -1 of this is the pass band, and beta will be varying like this. So, in the pass band beta varies like this when alpha is 0, and again here and here beta exists. Next, this characteristic impedance Zi is real in the pass band. What does it mean? It means that in the pass band power has to be transmitted. If Zi is not real, if it is imaginary, then no power will be transmitted. So, in the stop band it may be imaginary, but in the pass band it must be real. There can't be anything in between. Now, we will design a constant K filter. This is known as a prototype filter. The specifications are given like this. Suppose Z1 and Z2 are the two arms, series and shunt arms, then product of these two will be equal to some constant K squared. It has the dimension of ohms squared. Okay. Now, let us take a very simple example. Let us take this as an inductance L by 2 and L by 2 and a capacitance C. That is Z1 is equal to j omega L and Z2 is equal to 1 by j omega c. Okay. Then what will be Z1 Z2? It will be j omega L into 1 by j omega c, and that is equal to L by c, and that is equal to k squared. So, it is resistive, this product is constant. So, it is a resistive element, there is no j involved. So, you can write k squared as sum r k squared, all right, where r k is the resistance whose value will be root over of L by c. For a T network, we know the iterative impedance is root over of Z1 squared by 4 plus Z1 Z2. Okay. Let us compute this. This will be equal to root over of j omega L squared by 4 plus j omega L into minus j by omega c. Agreed? So, that comes to root over of L by c 1 minus omega square L c by 4. Okay. Now, so long as this is greater than 1, omega square L c by 4, this quantity is greater than 0, that is this quantity is less than 1, then this is always positive. So, ZIT will be equal to real. This is positive, means square root of that will be always real for this condition. Now, at the critical value omega c, this will be equal to 0. So, this will just cease to be real when omega c squared L c by 4 is equal to 1, or omega c is under root 4 by L c, that is equal to 2 by root L c. So, corresponding frequency will be 1 by pi root L c, so many hertz. Agreed? So, we find that for omega less than omega c, ZIT is real. Okay. And we can write, therefore, L, you see we had L by c as r k squared, and here we are having L c from here, okay, L c equal to 1 by pi square f c squared. So, if I take the product, L squared is equal to r k squared by pi squared f c squared, or L is equal to r k by pi f c. Similarly, c can be computed from either of them by substituting the value of L, r k pi f c. Okay. What will be the variation of alpha and beta from the expressions that we had earlier? We can see alpha in the passband will remain, this is frequency f, alpha will remain 0 in the passband, and it will be going up like this. It will be going up like this to infinity. Similarly, beta will be in the pass band, it will be falling to 0 like this. We will get the expressions for alpha and beta very soon. Therefore, Z I for a T network is root over of L by C 1 minus omega squared by omega C squared, and Z I T at omega equal to 0 will be just root L by C. Therefore, if I normalize this, I can write this as Z I T 0 into 1 minus omega square by omega C squared, or Z I T normalized, I can write this as Z I T normalized. Okay. Z I T normalized squared, if I am 1 minus, is this all right, omega squared by omega C squared Z I T was root over of this, and is this all right? So, I can write this, you can see if I normalize the frequency with respect to omega C, then I can write this as 1 minus omega normalized square. So, this is the equation of a circle. If I write omega n and Z I T n, then this is 1, this is 1. This is how Z I T varies. One may take a pi network and you will find that for a pi network it will be going up like this. I leave it as an exercise. One may derive the relation for Z I P similarly, Z I pi similarly. For a high pass filter, let us see the relationship. For a high pass filter, what we do, we take a capacitance in series and an inductance in shunt. So, if I have Z1 by 2, it will be Z1 is minus j by omega c. So, Z1 by 2 will give me 2c and Z2 is j omega L. So, here you are having, sorry, for a high pass filter in a T network, we have 2C and 2C, and an inductance L. This is for a T, and for a pi network we will have 2L and 2L like this. Okay. Now, what will be the relationship for the different parameters and the frequency? Z1 into Z2 once again will be L by C with the same logic, and then Zi t, for example, if I take, will be root over of Z1 squared by 4 plus Z1 Z2. Substitute the values for Z1 and Z2. So, you get L by C into 1 minus 1 by 4 omega squared LC. Once again, when this becomes 0, that is at the critical frequency, we get omega C as that frequency, which will make this 0. So, it will be omega C will be omega C squared will be 1 by 4 LC. Okay. So, if I substitute this here, it will be root over of L by C into 1 minus omega C squared by omega squared. Agreed? So, omega C squared is equal to 1 by 4 LC. Basically, it gives me a frequency FC equal to 4 pi root LC. There will be, if I take square root, it will be 2 root LC, and then 2 pi will make it 4 pi root LC. Now, if I use once again the same relationship, Z1 Z2, which is equal to k square R k squared, is L by C, and omega C is this. So, L comes out to be R k by 4 pi F C, and C as 1 by 4 pi R k F C. Okay. What will be the phase shift? What will be the phase shift and attenuation? Now, let us see the phase shift and attenuation for a constant K filter. For a constant K filter. Now, phase shift beta, if you want to compute, Z1 is j omega L and Z2 is minus j by omega C. Okay. You are taking the low pass filter, then what will be cosine beta? That is 1 plus Z1 by twice Z2. So, that gives me 1 plus j omega L by 2 into minus j by omega C. That gives me 1 minus omega square LC by 2. Okay. Cos beta is equal to 1 minus omega square LC by 2. So, cosine beta we can write as 1 minus twice sine squared beta by 2, and that is equal to 1 minus omega square LC by 2, and we also saw this to be equal to 2 into omega squared by omega C squared. Therefore, because if you remember, omega C square was 4 by LC. So, that gives me this. So, sin beta by 2 can be, you can equate these two, will be equal to omega by omega C. Therefore, beta equal to 2 sin inverse omega by omega C. Is it all right? So many radians. Okay. So, we may show this in the pass band it comes from 0, it goes to pi. Somewhat like this. This is omega c. Now, what will be the nature of alpha? Since Z1 by 4 Z2 is negative, in this case we can't use the first condition. It is not, we are taking two opposite elements, inductance and capacitance. So, Z1 by Z2 is negative. So, we can't use the first condition and we have to take the, that is beta equal to 0. If beta equal to 0, cos alpha we have seen is 1 plus Z1 by twice Z2. So, we cannot take this because cos alpha is always greater than 1, and if this is of opposite sign it will be cancelling. So, it will be less than 1. So, we have to take the other condition. So, this is ruled out. So, the other condition is when beta is equal to plus minus pi. So, that time cos alpha is minus 1 minus Z1 by twice Z2. This is the situation when Z1 and Z2 are of opposite sign. So, this will be minus 1 plus omega square LC by 2. If I substitute Z1 and Z2, I will get omega square LC by 2, which is 2 into omega square by omega c squared minus 1. And what is cos alpha? I can write this as twice cos hyperbolic alpha by 2 minus 1 cos squared. So, that is equal to twice omega square by omega c square minus 1. So, equate the two, that gives me cos alpha by 2 as omega by omega c, or alpha equal to twice cos inverse omega by omega c. So many Nepers. Okay. So, alpha varies this is omega c, alpha varies like this. It is in the pass band it is 0 and then it goes on increasing, but in the stop band the increase is not very rapid, it is according to this function. So, it will be gradually increasing. We want this rise to be very, very sharp. Okay. We want very good cutoff characteristics. So, we shall come back to that very soon. So, our aim will be for a steep rise in the value of alpha in the stop band. We will take it up very soon. Let us examine this for a high pass filter now. For a constant k high pass filter, what will be the variation of beta? Once again, for a high pass filter we have Z1 and Z2 like this. Z2 is omega L into j, Z1 is minus j by omega c. So, what will be cosine beta? It will be 1 minus 2 into omega square LC if I substitute the values of Z1 and Z2 in this expression. Okay. So, that is 1 minus 2 into omega c square by omega square. If you remember the expression for omega c was 1 by 2 root L c. So, omega c squared I can get 1 by 4 L c. So, that after manipulation gives me this. So, sine of beta by 2 in this case will be omega c by omega, or beta will be twice sine inverse omega c by omega. Okay. If you look at the earlier expression for a low pass filter, it is 2 sine inverse omega by omega c radians, and now it is 2 sine inverse omega, it is just inverse of the other one, so many radians. Let us see the expression for alpha. Cos alpha is minus 1 plus 1 by twice omega square L c. Okay. I have just put the conditions for Z1, Z2, etc., those values. So, we get this, that is minus 1 plus 2 into omega c squared by omega squared. So, this is nothing but twice cos squared alpha by 2 minus 1, that is equal to twice omega c square by omega square minus 1, or cos alpha by 2 is omega c by omega, whence we get alpha equal to twice cos inverse omega c by omega, so many Nepers. And what we got earlier was twice cos inverse omega by omega c. So, here also it is just reverse omega c by omega is obtained from the previous one, just by inverting it. So, alpha in this case will start from here, and then this is the pass band, it will be 0, and this is for a high pass filter. Okay. So, this is a stop band. All right. So, once again we want this to be very, very sharp. So, what should we do about it? We want alpha goes to infinity, very rapidly in the stop band. The characteristic impedance is real but not constant. In the pass band. It varies, as we have seen earlier. The characteristic impedance was gradually changing, the normalized value was changing from 1 to 0. So, in the pass band the characteristic impedance does not remain constant. We want that also to be substantially constant. So, we derive another type of filter from the prototype. We call it M derived filter. So, we have the same pass band and stop band, same pass band and stop band for this filter, but with a modified value of alpha, with modified alpha characteristics in the pass band. And its characteristic impedance should be identical. Then let us see what it will be like. Let us suppose we take a T network and we multiply Z1 by M. We are modifying Z1 by M, and that is Z1 dash. All right. So, if we consider MZ1 here, MZ1 here, MZ1 by 2, sorry, then what will be this Z2 dashed? Which will have an identical characteristic impedance. The two networks should have identical characteristic impedance. So, what will be Z2 dashed? Now, Z I, the characteristic impedance for this T network, will be root over of M square Z1 squared by 4 plus M Z1 and Z2 dash, which is yet to be determined, and that must be equated to root over of Z1 squared by 4 plus Z1 Z2, which means if I square them, equate them, Z2 dashed will come out to be Z2 by M plus 1 minus M square by 4M Z1. That means, if I have a low pass filter with an inductance like this and a capacitance like this was Z1 by 2, Z1 by 2 and this was C, we can have the M derived filter as M Z1 by 2. So, it will be M L by 2, M L by 2, is it not? M Z1 by 2, M Z1 by 2. If I take an LC combination like this, then it will be this one. And in the shunt element, it is Z2 by M. Z2 was a capacitance, so it will be M into C plus another element which is given here as 1 minus M square by 4M into Z1. So, since Z1 is an inductive element, so this additional element will be 1 minus M square by 4M into L. So, there is an inductance here. So, I rewrite ML by 2, ML by 2 and a capacitance and an additional inductance. Now, you see there is a change in the structure, there is an additional inductance that comes into picture, 1 minus M square by 4M into L. Now, what does it do? It gives me a resonating element. This resonating element, this resonance frequency can be so adjusted that it becomes a short at that resonating frequency, okay, that frequency can be adjusted, and at that time the entire signal gets shorted, there is no transmission. So, it becomes alpha equal to 0, there is no transmission of signal on this side. So, let us see alpha becomes infinity, alpha becomes infinity. So, at resonance frequency of this shunt term, that is omega infinity squared will be LC MC into 1 minus m square by 4m into L, which means 4 by 1 minus m square, m will get cancelled into LC. This is a frequency at which this will resonate. If m is less than 1, then this is positive, this is positive. So, omega infinity will be a frequency above omega c. See, 4 by LC is nothing but omega c squared. So, since m is a fraction, so this will be 1 minus something, this will be positive, but less than 1. So, it will be a frequency higher than omega c. So, omega infinity is greater than omega c. Now, we can adjust the value of m to get the desired value of omega infinity. What happens to alpha? This is our omega c. So, at some frequency omega infinity, alpha was going on increasing like this. Now, it will be shooting up to infinity at this point. Okay. So, this may be the gain of a prototype filter, sorry, not gain, the value of alpha, and this is for the m derived filter. If I put them in cascade, this will be m derived, after resonance again it will fall. So, if I put them in cascade, resultant alpha will be at omega c, it will be like this, and it will be practically going to infinity and then again fall like this. So, we get a very sharp rise in the value of alpha in the stop band. Okay. For a pi structure, we take Z2 dashed to be equal to Z2 by m. Then what will be Z1 dashed? That is, we have Z1 twice Z2 twice Z2, and we want to derive an m derived filter having the same iterative impedance, characteristic impedance. What should be this value? Z2 dash, Z1 dash. This we have taken as Z2 by m. So, it will be twice Z2 by m twice Z2 by m. So, once again we equate the two characteristic impedance. So, Z I pi squared, the expression is Z1 Z2 by 1 plus Z1 by 4 Z2, and on this side you will have Z1 dashed, Z2 dashed is Z2 by m, 1 plus m Z1 dashed by 4 Z2. Okay. If you multiply, cross multiply Z1 into 1 plus Z will get cancelled. So, Z1 into 1 plus m Z1 dashed by 4 Z2 equal to Z1 dashed by m into 1 plus Z1 by 4 Z2. Okay. From here, after simplification, we get this as sorry Z1 Z2 divided by Z2 by m plus Z1 by 4 into 1 by m minus m, which after simplification gives me, I can multiply by m. So, m Z1 into Z2 into 4m by 1 minus m square. One may simplify this, you can see for yourself Z2 by m plus Z1 by 4m into 1 minus m square. So, I have just divided by 1 minus m square here. So, divided by m Z1 plus Z2 into 4m by 1 minus m square. Okay. This has been just after adjustment of terms written like this. As if it is Z1 Z2 by Z1 plus Z2. So, it is a parallel combination. Okay. So, Z1 will be basically a parallel combination of m Z1 and 4m by 1 minus m square into Z2 in parallel, and then the shunt elements are twice Z2 by m twice Z2 by m. Okay. So, you can have the elements of L and C for a pi network, whether it is a high pass filter or a low pass filter. So, for a low pass filter, for example, we can have MC by 2, that will give me twice Z by M. This will be 1 minus m square by 4m into C. This one will be m into L, because it is m into Z1. If it is a low pass filter, then m into Z1 will correspond to m into L, and similarly here MC by 2. So, this is the M derived filter. The frequency, now the frequency omega infinity at which the attenuation will be infinity, that is alpha will be shooting up to infinity, will be corresponding to an anti-resonance frequency here. At resonance of a parallel circuit, this impedance will be infinite. So, there is no transmission of signal, it is virtually cut off. In the earlier case, it was shorting of the shunt element. The other way of getting it is where getting the same situation, that is the transmission is stopped, will be when the series element is cut off. So, at that frequency we will have omega infinity equal to, the elements are here. So, 1 by 1 minus m square by 4 m sorry, it is 1 by root L C, is it not? So, we put that value 1 by, it is m into L into 1 minus m square by 4 m into C. So, that gives me, is this all right? 2 by root L C into root over of 1 by 1 minus m square. This m will get cancelled, 4 will come here as 2. So, 2 by root L C 1 minus m square, and from here f infinity will be therefore 1 by pi root L C 1 by 1 minus m squared. Okay. So, from here this gives me f infinity also, f c also. So, this is f c by root over of 1 minus m square. So, m will be 1 minus f c by f infinity squared. For a pi section, therefore, omega infinity squared is 2 by root L C 1 by 1 minus m squared. This was for a T section, this was for a T section, and this is for a pi section. Okay. For a high pass filter, therefore, for T section we have 2c by m, 2c by m, because it is mz 1 by 2. So, corresponding reactance the elements will be capacitive elements of these values, and this will be L by m and a capacitance of value 4 m by 1 minus m square c. For a high pass filter, these elements will be capacitive, these will be normally inductive. So, I have an additional element C when we take M derived filter, and the pi section for a high pass will be similarly four m by 1 minus m square L, and this will be C by m, this is 2L by m, 2L by m. Okay. Let us take some examples. Suppose you are given Fc equal to 10 kilohertz, K equal to 600 ohms. That is 10 kilohertz means 10 to the power 4 hertz. So, what will be the values of L and C for a high pass filter? You are asked to design a high pass filter. What will be the value of L and C? For a high pass filter, we saw in terms of K, K means that Rk, okay, and Fc, this was the relation. So, it will be 600 by 4 pi into 10 to the power 4, so many Henries. Okay. Similarly, capacitance will be 1 by 4 pi K into Fc, that is 1 by 4 pi into 10 to the power 4 into 600, so many farads. Okay. Suppose you are asked to calculate, let us take another example, you are asked to calculate for a T section low pass filter, determine the frequency for which alpha, frequency f for which alpha is equal to 10 dB, f in terms of Fc, frequency f in terms of Fc. So, alpha is given as 10 dB, that is 10 by 8.696. If you remember, we discussed earlier the relationship between dB and NEPA. So, that comes to approximately 1.15 NEPA. So, alpha is equal to twice cos inverse f by Fc, that is 1.15 is twice cos inverse f by Fc. Okay. So, from here you can see f will be Fc into cos inverse 1.15 by 2, 1.15 by 2. So, this is a relationship between f and Fc at this frequency, at this value of alpha. Okay. So, we will stop here for today, and next time we will be taking up some more basic elements of graph theory, how to solve network problems with the help of graph theory. Thank you very much. Good evening, friends. Today we shall be taking up analysis of resistive networks, a computer aided approach using graph theory. So, we will be going back to the equations that we derived in our earlier lectures on graph theory. So, let us have a system of n plus 1 nodes and b number of branches. Then I can write the branch current vector as I1, I2 and so on, IB. Similarly, the voltage vector for different branch elements will be like this. Excuse me. If there is a voltage source, then we can write, so voltage source with a resistance R, then we can show each element like this. This is E, this is current I, this is R and this is V, the element voltage V. Then E plus V will be equal to R into I. If E is connected in the opposite direction, then it will be minus E plus V is equal to Ri. If E is connected like this. So, we get minus E plus V equal to R I. Thus, we can write E k plus V k equal to R k into I k, k equal to 1 to B. This is a generalized equation, and we can write in a vector form E plus V equal to R into 1 0 1 etc. Then you write R 15 20 15 and so on, the 6 diagonal terms, multiplied by 1 0 1 minus 1 1 0 and so on, 0 0 1 is BF transpose. So, it is a 3 by 3 matrix. Okay. So, I1 sorry, I dashed will be R1 sorry R dashed inverse, the inverse of this 3 by 3 matrix into E dashed, okay, where E dashed we have already computed E dashed as 100 0 100. So, whatever is the inverse of this matrix, that is the 3 by 3 matrix that we get, that multiplied by 100 0 100. So, that gives me I1 dashed, I2 dashed, I3 dashed. Once you have got this, compute vector I, that is BF transpose into I dashed, and BF transpose is known 1 0 1 minus 1 1 0 and so on, and that multiplied by I1 dashed, I2 dashed, I3 dashed. So, you get 6 values I1, I2 and so on up to I6. Okay. So, V you can compute minus E plus Ri, and hence P will be V1 I1, V2 I2 and so on. That will give you the branch power. Total sum of that will be equal to 0. Okay. So, sigma Vi II will be equal to 0. So, this you can check. Now, I have left the problem unfinished. I have just given you the hints how to solve it. You can try it yourself, you will get the result. Thank you very much.